Hi everyone, welcome to our fourth module for our CCNA Routing and Switching curriculum, Scaling Networks version 6.0, Networking 3 or LA1 subject under Engineer Ernie Pineda and Engineer Dennis Tacadena. For this week, we're gonna talk about dynamic routing. Okay, so moving on with our Module 4 objectives. First, we're going to look at dynamic routing protocols, and we're going to explain the features and characteristics of DRP. We're going to also compare and name the different types of routing protocol, particularly categorized as the distance vector dynamic routing and the link state dynamic routing. Okay, under distance vector, we're gonna take a look at how the protocol operate, and we will see how dynamic routing protocols achieve what we call the network convergence. We're going to also describe the algorithm used by distance vector routing protocols to determine what we call the network best path. Take note of those terms. Now we're gonna try and use those terms later as we go deeper with this discussion. And of course, we're going to identify also the different types of routing protocols under distance vector category. In addition, aside from the distance vector dynamic routing, we're gonna take a closer look also with the link state dynamic routing. Okay, under link state, we're going to explain how it works. We're going to identify also the algorithm used by this type of routing protocols to determine the best path. Same with distance vector dynamic routing. Okay, and also we're gonna explain how the link state protocol uses information sent in a link state update. So we're just gonna compare and contrast these two types of dynamic routing. Lastly, we're gonna explain the advantages and disadvantages of using link state routing protocols. Alright, so we're gonna cover all this learning. And then, of course, at the end of this module, okay, we're going to apply all these theories and this discussion to our packet tracer simulation activities. All right, so let's start. Okay, so we all learned in our past Cisco courses, particularly CCNA 1 and 2, that routers, okay, are network devices that are used to forward packets to and from a particular network address. Okay, so they are able to forward packets by using information stored in their routing table. Okay, that's how it derived its name, no? Routers, routing. Okay, so we also learned that routes to remote networks can be accomplished by the router in two different ways. Okay, namely, if you can still recall, we have two types of routes. Okay, the first one is, can you guess what it is? Alright, yes, static. Alright, we have the static route. And the other one is the dynamic route. Okay, the dynamic routing is the coverage of this module. Okay, but if you can still recall, no, the difference between the two. Okay, when you say static routing, it's also known as manual routes. Okay, wherein you tell the router exactly which route to take. Okay, by issuing a command, IP space route space the destination network subnet mask. Okay, Then it's either you use a next hop IP address or the exit interface. I believe that was our topic, no? Just before the lockdown, okay, last semester. Okay, so static routing, manual routes. Okay, so in this chapter we're gonna take a closer look, okay, on the other category of routing, okay, which is dynamic. All right, so basically it's just complete opposite of static. When you say static manual, this time we're gonna do dynamic. So in dynamic routes, we're gonna use different dynamic routing protocols to automatically, okay, to automatically allow our routers, okay, to find the best routes to and from a particular network. Okay, so that's our target. That's the target of this module. Okay, so this module, as I've said in our objective a while ago, introduces dynamic routing protocols. We're gonna explore the benefits of using DRP compared with when you are still using the static routing. Of course, if you know static routing, no, you are already aware of its disadvantages. Okay, since it's manual, so it has a lot of probably configuration that a network administrator has to carry it out. Now, since it is also manual, the procedure on how networks are being learned by routers are not automatic. Okay, so you see the difference now. Compared with dynamic, wherein once you run a particular dynamic routing protocol, okay, routers, okay, can use different algorithms, okay, embedded in those particular DRP, okay, to choose best path. Okay, what we're talking about here is letting the routers decide how they could reach the other networks using the most probable and the most efficient path. Okay, so determining the best path for network traffic. Okay, so that would be the in addition to our objectives a while ago, what we are going to cover on this module. Okay, so let's start off with taking a look at the different classifications of routing protocols. Okay, so as I've said a while ago, dynamic routing protocols are used to facilitate the exchange of routing information between routers. Now, let's define first what exactly is routing protocols. Okay, now a routing protocol, when you say routing protocol, it is a set of processes, okay, algorithms and messages that are used to exchange routing information, and it is used to populate the routing table with, for example, routing protocols choice of what we call best paths. Okay, now the purpose of dynamic routing protocol includes the following. Okay, so number one, okay, we already mentioned this one a while ago, discovery of remote networks. That is automatic discovery of remote networks. Number two, since we're running dynamic, means automatic, so it means that you maintain, or routers can maintain up-to-date routing information. So they themselves update their own routing table, okay, when they exchange routing information. Okay, next, using that up-to-date routing info, they can now choose the best path to destination networks, okay, and at the same time automatically finding, they gain an ability to find a new best path if, for example, a current path is no longer available. Now, as you can see in this graph, okay, routing protocols can be classified into different groups. Okay, this is actually according to their characteristics. Okay, so under the RP, okay, we actually have two types. The first one is the interior gateway protocols, or also known as the IGP. The other one is the exterior gateway protocols. Now, if we're going to divide this one, this first or the second row right here, and just below the DRP, is what we call as the purpose. Okay, the purpose of the DRP. So it can either be an IGP or EGP. Okay, the second row talks about the operation. Okay, operation. So under operation, so as you can see now, under IGP we have two categories. So right there you can see distance vector and the link state, which is the two main focus routing protocols under this module. Okay, so since we are focusing on these two types of routing protocols, okay, the other one or the other row after them is how are they classified, or these are the actual protocols under this routing category. Okay, so these are actually the protocols that is being run or on a router. So these are the protocols that you actually configure on a particular router. Okay, so each protocol, for example, the RIP v1, IGRP, they have what we call as a different behavior. So under behavior, we can classify them as either classful or classless protocol. Okay, we're going to talk about that later. Okay, just remember those terms. No, we have classful and classless type of protocol. Now, just to mention, no, the difference between the two. Okay, when you say classful routing protocols, okay, particularly the RIP v1, the old RIP v1 in the IGRP, these are legacy protocols that are being used. So as I've said a while ago, old. Okay, they are being utilized on older networks. Okay, now this protocol, for example, the RIP v1, okay, has evolved into a much better classless routing protocol, which is the version 2. Okay, IGRP on the other hand has evolved into a much better version, okay, the enhanced IGRP. Okay, so this is under distance vector routing protocols. Now on the other hand, we have the link state. Now under link state routing protocols, okay, we have the OSPF. Okay, this one right here. So we have the OSPF, and then we also have the ISIS. Okay, actually, the remaining modules that we're going to cover in CCNA3 will focus on a deeper understanding of both EIGRP and OSPF. Okay, so that is for modules. They have separate discussions. Now for modules 5, I think, is EIGRP, while module 6 and 7 is all about OSPF. Okay, so it's just gonna cover a deeper discussion of this particular dynamic routing protocols. Okay. Okay, let's have a concrete definition. Okay, first of both IGP and EGP routing protocols. Okay, so when you say interior gateway protocols or IGP, okay, this is the protocol that is used for routing within an autonomous system or AS. So when you say AS, it is a collection of routers under a common administration, such as, for example, a company or an organization. Okay, let's say Mabalacat City College. Okay, that is an autonomous system. It is where we use the common routing protocols such as the RIP, EIGRP, OSPF, and ISIS. Okay. Again, no, typical examples of an autonomous systems are, let's say, a company's internal network, or also an ISP's network. Okay. The internet itself, no, the internet itself is based on the autonomous system concept. Okay, so therefore it doesn't work with just IGP alone. Okay, so that's where exterior gateway protocol uh, comes in the picture. Okay, so EGP on the other hand is used for routing between AS. Okay, so remember that, no? IGP used for routing within an AS. So routing within an AS, autonomous system like company, organization, it can also be a routing domain, okay, autonomous system. Okay, so that's where IGP is used. Okay, EGP on the other hand, okay, is used for routing between those autonomous systems. So example of that is the BGP, all right, or Border Gateway Protocol. Now, unfortunately, in this module, BGP is not beyond the scope of this course. Okay, so we're going to focus uh, deeper, or we're going to focus particularly on this IGP categories. Okay, specifically the EIGRP and OSPF. Okay, so that's the difference between those two categories under the IGP and EGPs. Now, moving on, we're going to differentiate, okay, the routing protocols under IGPs, because as a network administrator, it is, let's say, it's more considerable that you will be configuring the autonomous system routing within your company's network or organization's network. So you will use either the RIP-v2, EIGRP, OSPF. Okay, that's why we're going to focus more on these categories. All right. Now, let's move on with discussion of. Let's start off with the distance vector. Okay, so let's have that slide. Okay, so let's define first what is a distance vector routing protocol. Okay, so distance vector is actually two words, no? Distance means you're just basically identifying how far it is from the destination network, and it's based on a metric. Okay, distance, how far. So it is measured using metric such as number one, we call it the hop count. Okay, remember that. So metric, hop count. Okay, cost. Okay, bandwidth and delay. All right. So again, no, distance identifies how far it is from the destination network based on a metric such as hop count, cost, bandwidth, and delay. So for example, this is our source network. Okay, source network coming from R1. All right, and then our destination network is our source. Our destination network is R2. Okay, so when you say, let's say, hop count, okay, we're going to use hop count as our distance. How many hops, okay, will R1 users from R1 take so that they can reach the networks that belongs to the R2 network? Okay, next, that is the distance, right? Okay, next, the other term is vector. Okay, what exactly is a vector? Now it says here that vector specifies the direction of the next hop router or exit interface to reach the destination. So vector is the direction. So for example, again, no, if this is your source, this is your destination, so your direction is from and coming from R1 going to R2. Okay, now if R2 will send packet, okay, from this network going to that particular network, okay, they will switch roles. So R2 will now be the sender, okay, going to R1. R1 now will become the destination. Okay, and then of course, we already discussed the principle of the next hop, router, next hop, and the exit interface. So that is commonly used whenever you try to configure, let's say, a static route. Okay. Okay. Now, there are 4 distance vector IPv4 IGBs. Okay. So these are, okay, we have the RIP v1. Okay, the legacy, the old RIP version 1. Actually, in most companies, they do not require, or they do not encourage, okay, using the old RIP v1 anymore. Okay, we're going to talk more about that in terms of its disadvantages later. Next, we have the version 2, okay, of that RIP. We also have the IGRP, okay, the old IGRP, which is already obsolete and is now replaced by a much better EIGRP. So, for example, let's say when you encounter a question, okay, which of the following are distance vector routing protocols? So, just make sure that the choices here, okay, are chosen whenever you try to identify, because these are examples of distance vector routing protocols. Okay, so we have the RIP, the IGRP, and the new EIGRP, advanced version of the distance vector routing. Okay. Okay, so though distance vector routing protocol is very simple to configure, okay, its main disadvantage is that whenever you use distance vector, or whenever you try to choose distance vector routing, it only grants the router knowledge in terms of the distance between vectors. Okay, or the only information a router knows about a remote network is the distance or metric to reach the networks. Okay, it doesn't have any knowledge, or routers running distance vector doesn't have any knowledge of the entire path, okay, to a destination network. Remember that. Okay, it doesn't have, let's say, in an analogy, it only knows the distance from R1 going to R2, okay, but doesn't exactly know or have the entire map of the network. Okay, so it just knows that in order for R1, for example, to reach R2, this will be the metric available. Okay, it will only take me 1 hop, for example, 1 hop from R1 going to R2. Okay, so again, distance vector routing protocols do not have a map of the entire network topology, unlike any other types of routing protocols do. Okay. Okay, now let's take a look at its counterpart. Okay, the link state routing protocol. Now, in contrast to distance vector routing protocol operation, if a certain router is configured with a link state routing protocol, it can create a complete view. Okay, so it can create a complete view or map or topology of the network. Okay, so it can create a topology map of the entire network. Okay, how? By gathering information from all of the routers. So they will exchange what we call link updates, okay, or link state protocol updates. Okay, now I forgot to mention that in distance vector routing protocol, it uses what we call as periodic updates. Okay, So routers running distance vector routing protocols exchange information periodically. So let's say, for example, every 30 seconds, they will send an update of the routing table to their neighbor routers to tell other routers that these are the networks that are currently configured on my interfaces. Okay, that is sent periodically. Okay, periodic. Okay, um, whether there are changes or no changes with when it comes to the networking size or network addresses. Okay, still routers running distance vector routing send that periodic update. Okay, now in contrast, okay, link state routing protocols do not use periodic updates. Okay, so they do not send periodic updates, unlike distance vector. Okay, so how do they exchange routing information? So instead of periodic updates, in link state, updates are only sent when there is a change in topology. Okay, when there is a change in topology. So for example, let's say in this given network, okay, everything is running well, and then you already run a link state type of routing protocol. Okay, so they will exchange information, but not periodically. Whenever a certain network goes down, so whenever there's a change in the topology, okay, for example, this network right here that is connected to R1 goes down. That is the time that R1 sends the update. Okay, we call that triggered update. All right, so link state routing protocols use triggered update. Okay, triggered update means that they're only sent when there is a change in the topology. Change in the topology means, for example, if there is an added network, okay, there's an additional network that was configured on a certain router, or a certain network becomes down. All right, so triggered update. Okay, unlike distance vector that uses periodic update. Okay, remember that. Now, under link state routing protocol, if you want to run link state, so it's either you use OSPF and ISIS. Now, the coverage for CCNA3, again, as I've said a while ago, will only cover the EIGRP for distance vector and OSPF for link state. That will be for the remainder of the module for this semester. Okay. Okay, moving on. Now let's talk about the difference between, okay, I mentioned this two terms a while ago. Okay, classful and classless routing protocols. Okay, so just to define what classless and classful is, okay, when you say classless routing protocols, it is actually the sending, okay, sending of routing information, which includes the subnet mask. All right, whenever they exchange routing updates. Again, no, we have two types of routing updates. Okay, from my previous slide. So we have number one is the periodic update that is being run by distance vector types of routing protocol. The other one is the triggered, okay, triggered update, all right, which is being run by the link state type of routing protocol. Okay, now we're gonna see the differences and advantages between those two types of updates. Now, using those updates, okay, whatever is inside those information, okay, when you say classless, again, it includes the network address along with the subnet mask. Okay, we will see the importance of that inclusion later. Okay, when you say classful, on the other hand, okay, classful, okay, in contrary with classless that includes subnet mask, classful protocols do not send subnet mask information. Okay, no? So classful does not send subnet mask information when they exchange routing update. Okay, now the problem with classful routing is that whenever they exchange information and then this protocol does not include the subnet mask, it can create problems, especially with discontiguous networks. Okay, I'm going to give examples of discontiguous networks later. Okay. Another disadvantage is that when you use classful routing, it cannot support what we call as the VLSM. Right? So it doesn't support variable length subnet masking, okay, as we learned in CCNA1. And also the routing called the CID, or classless interdomain routing. Okay, I'm gonna show you a sequence of slides later to explain this better. Okay, but for now, I just want you to remember, okay, the terms, no? Classless, all right, include subnet mask in the routing update. Classful doesn't include subnet mask in the routing updates. Okay, what is the impact of not including the subnet mask information in the routing update? It can create problems. So we're gonna see those types of problems later in a discontiguous networks. Okay. All right. So to better understand deeper, no, the difference between classless and classful routing protocols, their advantages and disadvantages. Okay, let's have this network simulation. Okay, so for example, we have R1, R2, R3. Okay, we have the following networks indicated here. All right. We have 172.16.10 network. In the middle, we have the 192.168.10 and then the 20 network here, and the 172.16.20 network on the other side. So in total, we have, as you can see, 4 networks. So let's assume that all these routers are running RIP. Okay, RIP, okay, is a classful type of routing protocol. Okay, so again, classful doesn't send or doesn't include subnet mask information in the routing update. So we're going to see the impact of the negative impact of that using this sample topology. Okay, so let's say, for example, R1's time is up. So it will now send a routing information to the other neighbor. So as you can see, it has 2 networks connected to it, the 172.16.10 and then the 192.168.10 network. Okay, so when R1 sends routing information update to the other routers, okay, it will send the network information that is directly connected to it. So in this case, it will send the 172.16.1.0 network. But as you can see, no, instead of sending the 1.0, since it doesn't include the subnet mask, okay, it did not include the subnet mask. All right. Okay, it only forwards the class B network address automatically. So the router will just categorize this as class B address. So it doesn't include the subnet mask. So it's just gonna send the 172.16.00 network. As you can see, there is already a problem there. So instead of sending the 1.0 network, it automatically detects the class B network and forwards it to the other neighbor router. Okay, so when R2 receives and processes that updates, so let's see that. Okay, so when R2 receives and processes that update, it will now create an entry on its routing table for the class B network, which is the 172.16.0. Okay, network on its routing table R2. So it will, since the update came from R1, so it will record that particular network. Okay, so as you can see, we already have some trouble here because instead of recording the 1.0 network, it automatically reverts to class B, which is 172.16.00 network. Okay, did you notice that? Okay, next. Okay, this scenario at the same time shows that when R3, okay, R3 on this side forwards an update to R2, Okay, it also does not include the subnet mask information. So instead of sending the 172.16.2.0 network, it will revert to automatic classification of this address into class B by not including the subnet mask, because that is the behavior of classful type of routing. It doesn't include the subnet mask. So instead of sending the 172.16.2.0 network, okay, it sends the 172.16.0.0 network. Alright, so when R2 receives that information, okay, it actually receives the same network address, okay, and then records it on its routing table. But as you can see, no, that's the same network address that was sent by R1. Okay, so they will just have a different interface, okay, from which that network address came from. Now this scenario right here, so you don't see two networks now. Instead, you only see one network. Or in fact, we already have two networks that supposed to be updating the R2's routing table, but instead we only see one. Okay, that is because when there are two entries with identical metrics in the routing table, okay, the router shares. Okay, remember this now, the load of the traffic equally among those two links. Okay, that is also known as load balancing. Okay, now by just looking at the routing table, definitely you will notice that there's something wrong. No, so when you look at this figure right here, so when you try to ping, for example, let's say from R2, I'm going to try to ping any computers on this network. So I'm gonna ping 116.1.1. So probably that is yeah, the R1 or the G00 port on this R1. Okay, as you can see, no, it will have a negative impact. Okay, because it doesn't know exactly which is 171.1 address. Okay, because of uh, the entry on its routing table. Okay, so it definitely has a negative effect on its connectivity, because instead of, again, no, instead of looking at two networks, okay, learned via RIP, okay, it combined the same identical entries, no, especially if they have the same metric. Okay, it combined them into a certain routing table entry, which is very confusing for R2. All right, because it can go this way, it can go that way. Now let's take a look at what if we're gonna run classless. So let's take a look at the difference, no? Now, in fact, when you talk about classless routing protocols, no, particularly in modern networks, they no longer use classful type of IP addressing. So I just showed you a previous example on how old networks works. Okay, but right now, as we speak, no, modern networks do no longer use that type of classful routing. Okay, so in this scenario, we're gonna try to simulate um, a forwarding of routing update using classless type of routing. Okay, so classless IPv4 routing protocols. Um, if you wanted to run this one, of course, you have a selection. Let's say you have the RIP v2, the version 2 of the old RIP 1 a while ago. You also have the AIGRP, OSPF, and the ISIS. Okay, so all of these protocols includes the subnet mask information along with the network address when they exchange routing updates. Okay, at the same time, classless routing protocol supports VLSM. Alright, so and also the CIDR, the one that was mentioned a while ago. Alright, so the classless interdomain routing. Okay, so let's take a look at the same scenario. Okay, but this time we're gonna run classless update. Okay. So this one is a discontiguous network design. So as you can see, we have different types of network addresses. Okay, so let's say we're gonna run RIP version 2. Okay, again, RIP version 2 is a classless type of routing protocol. Alright, so when it's time for R1 to update its neighbor, so using classless, as you can see, no, unlike Classful, in this scenario, it included the subnet mask. Alright, so it extracted the exact network address. Since we have subnet mask, we have full control of that network address. So it includes the subnet mask information. So it sends the 1716 exactly, the 172.1.0 network across its router neighbor. Now, when router 2 receives that routing information update, okay, it adds this particular entry. Okay, so the first entry, as you can see, we have two entries, no? The first line, as you can see right here, displays the Classful network address. Okay, like with the this is vector a while ago, no? But this time, it also added, okay, it also added the network address with the subnet mask value. Okay, this is also known as the child route. Okay, the parent route is the 172.16.0.0. This one right here is the also known as the child route. Okay, it also includes the exit interface. Okay, so where did that update came from? It came from S000 of R1, that is the exit interface. Okay, or sorry, sorry, the exit interface. Okay, and the address that it came, the update came from as well. So as you can see, no, it came from R1 going this direction, that is the vector. Okay, so we have this routing entry right here. So this one already has the concrete network address. Okay, unlike the one that we have in the Classful routing information a while ago. Okay, moving on. Okay, in the same instance, okay, let's say R3. Okay, R3, okay, forwards an update to R2. Okay, using RIP v2. Again, it includes the subnet mask information with the update. So it gets the entire network address 172.2.0/24. Now, when R2 receives that information, okay, it adds another child route entry of 172.16.2.0. Okay, so you notice that this is actually the one that we wanted to see on the routing table, having identified R2 having to identify two network or two remote network addresses. Unlike in Classful entry a while ago, wherein it only has one routing entry, which is very confusing for that particular router. Okay, this one has a concrete, exact network address. So the 172.16.1.0, alright, via the next hop. Okay, next hop IP is 192.168.1.0. Let me just open my marker. So in order for R2 to reach this network, okay, it will have this next hop address, that is 192.168.1.1, alright, via the serial exit interface. Alright, okay, serial 000. Now, in order for R2 to reach the other network, okay, on the other side, okay, so you can see that one right there, 2.0. Alright, the next hop IP address is 192.168.2.1. So next hop from here are two, next hop, that one right there. And if I'm going to use my exit interface, so that is S001 exit. So it is displayed in full detail. Okay, the routing table is concrete, right? So if you're going to check, okay, if we're going to run, for example, let's say we're going to try and ping, okay, from R2, we're going to try and ping 172.16.1.0 network. Okay, that is the interface right here. All right, since we have a complete updates on those network recorded on its routing table, then you assume, or um, we expect that the ping request will be successful. Okay, so when you try and ping, for example, on the other side, when you ping 172.16.2.1, we expect that you get the same successful result because the routing table is much better, or it's complete compared with what Classful routing protocols showed us a while ago. All right, so yeah, that is the difference between the two. That's also the main reason why RIP and IGRP are now obsolete, particularly on these modern networks. Okay. All right. So moving on. Okay. So on this table, we're just gonna have a summary on the comparison between the different routing protocols and their categories. No. So first up, we have the distance vector group, and then we have the link state group. Okay, so let's just compare, no? Number one, in terms of the speed of convergence. So when you say speed of convergence, this actually defines how quickly routers in the network topology that shares routing information reach a state of consistent knowledge. Okay, so the faster the convergence, the more preferable the protocol is. Okay, so as you can see right there, no, RIP v1, RIP v2, IGRP. Look at that. That's why this is the main reason why these protocols are already obsolete nowadays. All right. So right now, as you can see, no, in terms of industry standards, okay, these two protocols or these three protocols right here are commonly used because of their fast convergence characteristic. Okay, next next we have the scalability. Okay, the scalability defines how large a network can become and how large a certain routing protocol can support a particular size of network. So as you can see, okay, again, no, disadvantages of these three existing or these three old protocols, they can only support small networks. Okay, so right now, no, in terms of modern networks, we are expecting large networks. So it's better to use these two types of dynamic routing protocol. Use of VLSM, okay. RIP v1, no. This one is in terms of Classful. So if you remember, the Classful uses VLSM. Classful, no. Classless, yes. Classful, classless. So it includes the subnet mask. So that one right there. Okay. The only advantage of probably the old protocols is their resource usage. Okay, so resource usage includes the requirements of routing protocols such as the memory space, the RAM, the CPU utilization, the link bandwidth utilization. So in that scenario, the old protocols has an advantage because they are low in terms of resource usage. Okay, EIGRP medium, OSPF uses high resource usage. That's why if you're going to implement, if you choose to implement OSPF, just make sure that your routers can support it, or probably has higher RAM, okay, or the newly released routers from Cisco, okay, so something like that. Implementation and maintenance, okay, RIP v2, very simple. Okay, EIGRP and OSPF, again, in terms of disadvantages. So this is where EIGRP and OSPF comes into play in terms of the disadvantages, no? In terms of implementation and maintenance, because it requires an additional level of knowledge for a certain network administrator to implement and maintain. Unlike RIP V2, that's just pretty straightforward. Okay, easy to implement and easy to maintain, right? So this one right here. Okay, moving on, let's take a look at routing protocol metrics. Okay, so routing protocol metrics. Okay, now what exactly is metric? So when you say metric in routing protocol, it is a measurable value that is assigned by the routing protocol to different routes based on the usefulness of that particular route. Okay, so measurable value. Now, a certain routing metrics are used to determine the overall cost of a path from source to destination. So imagine the term cost. When you say cost in networking term, we can say that that is the distance. All right, the distance of a certain path from source to destination, or for example, from point A to point B. Okay, the distance from point A to point B. Now, remember, different routing protocols use different metrics. Okay, again, different routing protocols use different metrics. Okay, we're going to discuss them one by one later. But when you talk about cost, again, going back to cost, okay, the best path is always, take note of this one, the best path is the route that is always having the lowest cost. All right, so the best path is the route. Okay, so the best path is actually the one that is being chosen, no, by routers depending on what particular routing protocol do they use. Okay, because their metric computation behaves according to their routing protocol implementation. Okay, so again, no, best path is the route with the lowest cost. Okay, now let's take a look at the metrics, no, used for various dynamic protocols. Okay, RIP uses hop count. Okay, RIP uses hop count. OSPF uses cost based on cumulative bandwidth. Okay, based on cumulative bandwidth. While EIGRP uses bandwidth, either bandwidth, delay, load, and reliability. Okay, so we're gonna have a simulation of this one to show you the metrics used by different dynamic protocols and which best path will they choose according to a certain protocol that they are running. Okay, so we're gonna see that on the next slide. Okay, so let's have this simulation. Okay, so for the first scenario, we're gonna use, let's try and assume that R1, R2, and R3 are using RIP. Okay, so when you say RIP, okay, again, the metric used by RIP is hop count. Hop count. Okay, so for example, let's say this would be our source network. This would be our destination network. Okay, so if you're running RIP, okay, RIP, okay, RIP uses, okay, or RIP chooses the best path based on hop count. Okay, hop count. Okay, from source to destination. Okay, so if we're going to count the hops, okay, we count the hops per routers, right? So we learned that in CCNA1. So if you're gonna go this way using RIP, that is one hop, one. Okay, to reach PC2, okay, you have 2. Okay, so you have 1, 2, total of 2 hops. Okay, if you're going to go this way. Okay, that is the metric for RIP. So these 2 hops right here, RIP will try to compare that. So what about, for example, using this line right here? So to reach network, PC2 network, going this way will only take me how many hops? One hop. Okay, so if you're running RIP, so which best path? Okay, which of these two available path will RIP considered as its best path? Okay, so obviously it's the one with the lowest hop. Okay, so what we'll do if you're running RIP, so it will go this way exactly to send that packet. Okay, now on the other hand, if we are using OSPF, alright, OSPF chooses base path based on cumulative bandwidth. Okay, cumulative bandwidth, it means the speed on the line. Okay, so let's analyze the network. As you can see right here, this line, though it only has one hop, if you are running OSPF, it only has 56 kbps in terms of the bandwidth. Okay, this line only has 56 kbps. This line right here is a T1 interface, so it means it's faster compared to 56 kbps. Okay, T1 line, T1 line. So these two lines right here are faster compared with this line. So if you're running OSPF, its algorithm tells the router that when he chooses the best path, it will base its decision on the bandwidth available. So which is the fastest bandwidth? Okay, so let's try to run OSPF. So if this is running OSPF, definitely it will choose, okay, the path that has the higher bandwidth. All right, so again, no, we're talking about dynamic routing protocols behavior in terms of choosing the best path. So they are relying on the metrics that was pre-programmed for them to select. So if you're running RIP, it will choose the best path based on the number of hop counts. So whether that line is slow or fast, it doesn't care. Okay, so it will just focus on the number of hop counts. So the lesser the hop count, that's how it based its decision on choosing the best path. OSPF, on the other hand, behaves differently. Okay, so no matter how many hop counts it would take, as long as as long as it finds the line that has higher bandwidth, then it will choose that line. All right, so it's called cumulative cost or cumulative bandwidth based from source to destination. Okay. Okay, so before we proceed with the discussion of dynamic routing protocol operation, let's have a simple understanding check first. Okay, this activity covers the past discussions, okay, or the current discussions that we are talking about when it comes to different dynamic routing protocol characteristics. Okay, let's start off with this first activity. Okay, wherein you're going to classify dynamic routing protocols. All right, so we have, I think this was based from the graph that was shown a while ago, okay, or earlier this module. So we have under DRP categories, okay, interior gateway protocols. Under distance vector, can you fill in the correct categories or the correct types under distance vector routing protocol? So we have given is the IGRP right here. So the enhanced version of IGRP, here are the choices. All right, correct. So we have the EIGRP. All right, and then the other one, okay, what is the other type of distance vector routing protocols aside IGRP? Okay, if you answered RIP v1, okay, let's check. And of course, the enhanced version of RIP v1 is the version 2. All right, so yeah, let's check if your answers are all correct. There you go. Okay, so these are the correct classifications of distance vector routing protocols under this categories or under this protocol. Okay, next. Okay, what about link state? So, which amongst these choices, all right, is considered as or under link state routing protocols? We have two. All right, so we have OSPF and the ISIS. Okay, correct. Next. Okay, what about path vector routing protocol? We only have one path vector. Okay, correct. So we have the BGP or border gateway protocol. All right, yeah. So that is okay. We successfully classified the RP according to their category. Okay, whether they are link state, distance vector, or path vector routing protocol. Okay, let's proceed to our next activity. How about this one? Okay, so we're gonna try and compare routing protocols, okay, in terms of their characteristic. So we have clues here on what answers to choose: slow or fast, small or large, yes or no, and then the rest. Okay, so let's start off with RIF V1 and IGRP. All right, in terms of speed of convergence, are they fast or slow? All right, so since these are the legacy, all right, legacy means older version of routing protocols under distance vector. So yeah, they are both slow. So we're just gonna check the answers one time later. Scalability of network. Okay, which size of network do they support? RIP V1 and IGRP, small or large? What do you think? Correct. So they can only be used on small networks. So yeah, we'll see later. Okay, supports VLSM, variable length subnet masking. Okay, it includes, or do they include the subnet mask whenever they exchange routing information? Yes or no? Yeah. So we have no. What about resource usage? So you have three options here: high, medium, or low. Okay, so if you answered low, we'll see later. The implementation and maintenance. So is it simple or complex? All right, so let's see. No, simple. Okay, so yeah, so this is about RIP V1 and IGRP routing protocol characteristics according to different categories. So let's check if your answers are all correct. Yeah, right there. Okay, so yeah, I think these are the common or the basic understanding or the basic characteristics of both RIP V1 and IGRP. All right, when asked about their protocol characteristics, okay, categories. All right, next, let's proceed with the other routing protocols. Okay, what about the enhanced version? Okay, let's find out. Okay, RIP V2 and EIGRP. Speed of convergence. Okay, with the enhanced version, is it slow or fast? All right, so this time is fast. Scalability of network. Okay, so contrary with the older version, okay, that can only support small sized network. So this time, okay, we can say that they both RIP V2 and IGRP can support large network. Supports VLSM, yes. Resource usage. What about resource usage? High, medium, or low? Okay, let's start off with medium. Okay, implementation and maintenance, simple or complex? What do you think? Let's start off with simple. Then let's just check our answers later. So, it's don't worry if we get the wrong answers. So this is just an exercise. So we should go compare our answers later, and then if they are wrong answers, then we're just gonna change them according to the choices right here. So let's check. See. Okay, so we have several wrong answers. Okay, so let's try and fix that up. Okay, for RIP v2, okay, though it's still an enhanced version of RIP v1, alright, it's still considered as slow in terms of convergence. In terms of scalability of network, though it is still already an enhanced version of RIP, okay, still it doesn't support large network. Remember that, alright? They both support VLSM, so that is yes. Resource usage, okay, EIGRP, an enhanced version of IGRP, medium, that is correct. But what about RIP v2? We answered medium, but it is incorrect. Okay, so yeah, we might as well change it to low. Alright, RIP v2, correct. Our answer in terms of implementation and maintenance is simple. What about EIGRP? Alright, so the enhanced version, okay, in terms of implementation and maintenance, okay, has added complexity compared with the RIP v2. Alright, so let's check now if the revised answers are correct. Okay, right there. Okay, so again, no, just try and remember the differences in terms of their characteristics and their categories. Alright, so again, even if RIP v2 is already an enhanced version of RIP v1, there are still disadvantages in using it. As you can see, no, it still has slow speed of convergence. It still supports small size networks. Okay, so if you probably have a larger network compared with or on your autonomous system, so you might as well choose EIGRP rather than RIP v2, alright, or RIP version 2 protocol. Alright, but in terms of the only advantage of using RIP v2 is in terms of implementation and maintenance, and of course, the usage in terms of resources. So probably if you have older routers with just enough amount of RAM, then you might just go with RIP v2, alright, because it consumes lower resources. In terms of implementation, yeah, right there. Okay, so RIP v2 is just very simple to implement. Okay, so that is, I think, the advantage compared with the EIGR. Okay, so yeah, it actually depends on the process on which protocol to use on your network. Actually depends on first foremost probably the size of your network. You want to run the RP, right? And probably the equipment or the available equipment, routers, in terms of resources and their capability to run a particular particular protocol properly or efficiently. Okay, so yeah, this is the correct answers. Let's move on with the other activity. Alright, so this time, okay, we're gonna compare routing protocols, OSPF and ISIS. So this is a link state type. So speed of convergence, slow or fast. Okay, so OSPF, to start off with the fast. Scalability of network, small or large. Choose large here. Supports VLSM, of course, both of them supports VLSM. Resource usage, OSPF. Alright, so you're thinking high. Implementation and maintenance. Okay, I'm gonna choose complex here. Alright, so let's check both of them. Huh? So let's see if the answers are correct. Alright, right there. So you can probably see that the answers in terms of its comparison, in terms of its characteristic, both OSPF and ISIS are identical, right? So in terms of convergence, definitely OSPF is fast. Okay. Large size networks, yes, it supports large size networks. That's why if you're going to pick out a DRP out of the three available DRPs, RIP2, EIGRP, OSPF. Okay, you have OSPF on top of placing it on top of the list. Okay, just make sure, okay, that your routers must be able to support OSPF functions as well. And in terms of implementation and maintenance, okay, your network admin should be well trained, okay, and are familiar with how to implement or the implementation procedures of OSPF, especially when you're gonna run multi-area OSPF. That is that is a topic on the next succeeding modules. Okay, so all right, good job on this activities. Let's move on. Okay, so we have another one. Okay, so this time we are asked to match the metric to the protocol. Okay, so we have the three given protocols here: EIGRP, OSPF, and RIP. So we talked about metrics a while ago, and then we found out that each protocol has different metric scenarios, okay, or uses different metric whenever they choose the best path. Okay, so let's find out. The first one, data type description, metric based on hop count. So which among this protocol uses hop count? All right, if you answered RIP, okay, let's find out later. Uses cost as its metric. The cost is a cumulative link bandwidth. Okay, OSPF. Okay, what about the protocol that uses metric based on delay and bandwidth? Delay and bandwidth. All right, EIGRP. Metric can be based additionally on load and reliability. Probability of link failure based on load. So yeah, let's start off with EIGRP. Okay, for that answer right there. Okay, so let's check. All right, yeah, so we got them all correct. So I guess you've been listening pretty well with the answers or with the discussion on this particular metrics. Okay, good job, guys. Let's move on. All right, so yeah, that ends our activities, short activities. Okay, I hope you've got all the answers correct. Okay, so moving on with the final topics for this module. Okay, we're just gonna try and discuss the different dynamic routing protocol operation. Okay, so in here we're gonna try and observe how routing protocols exchange information, okay, that are contained or saved on their routing table. So take note, okay, guys, in order for a router to successfully map or discover remote networks, okay, as we've discussed previously, no, they exchange routing information. Okay, that routing information is stored on their routing table. Okay, that's why we call it routing table update. Okay, that's why distance vector do this by sending periodic updates. Okay, every 30 seconds, send. 30 seconds, send. Okay, link state do it differently. Okay, so link state sends triggered update. So instead of sending periodic, link state routing protocols sends it whenever there's changes or whenever there's a change on the network topology. All right, so it is not a periodic update compared with distance vector. So we're gonna see that here in action. Okay, so we have the sample topology. Okay, we have two routers. And as you can see, no, if you count the number of networks, we have 1, 2, 3. Okay, again, going back to the principle of counting networks. Okay, those three networks are 172.16.10, 16.20, and 16.30. All right. So you notice that R1 already has two directly connected networks to it. Okay, guys, CCNA2, no? if you remember the discussion in identifying directly connected networks and remote networks. So in total in R1, we have two directly connected networks. Let me show my sorry, let me just show my pen. Okay, so we have two networks directly connected with R1 router. Okay, so let me just show my pen. So we have the 16.10 network, 16.20 network. So these are directly connected networks. So from R1, we only have one remote networks, that is the 3.0 network. So we're going to need routing information or routing update from R2 so that R1 can learn and can reach that particular network. Okay, so let me just play this one so that we can see it. So routing protocols are used to exchange routing information between routers. So let's see how did that happen. Okay, so R1 will save these two networks right here that is directly connected to it and then send that updates to R2. R2 will receive and process that information and then save the information on its routing table as well. Then after that, it will create its own update, okay, saving the directly connected network on that routing update and then send it across R1 as well. So that's how they exchange routing information, okay, so that each router can learn about remote networks. All right. Now, simultaneously, no, when a router detects a topology change, okay, for example, let's say I added a network here. Okay, I added 172.16, all right, 4.0 network. I added another LAN on R2. Okay, automatically, since, for example, they're using distance vector every 30 seconds, okay, that network information will be added to the routing update of R2 so that it can tell R1 that I have a new network connected on my LAN. Alright, so that R1 can be aware of that or will be aware of that network. Okay, so that's how that's the process on how they exchange routing information. Okay, so moving on. Alright, so this time we have a bigger topology. Okay, so if you're going to count the number of networks here, what do you think? How many networks do we have? Alright, so we have 1, we have 2, we have 3, we have 4. Alright, so 4 networks in total. Okay, if you're going to look at R1, alright, how many directly connected networks do you have? You have 2. Okay, R2, how many directly connected networks? You have 2. R3, how many? You also have 2 directly connected networks. Okay, so if you're going to look closer, what about if you're going to count the number of remote networks? So from R1, how many remote networks do you have? Remote means these are the networks that are not directly connected to that particular router. Alright, so we have R1 remote network. Yeah, correct. You have the 3.0 and then the 4.0. Okay, these are considered as remote networks to R1. So you're going to need a certain routing protocol in order for R1 to reach those networks. Okay, now if you're going to follow the same procedure, okay, for R2, how many remote networks do you have? You have 2 as well. The 10.10 and then 10.40 network. The networks that are not directly connected to it. Okay, same principle with R3. Alright, you have remote networks 10.20 and 10.10. Alright, so remember the principle on how to identify directly connected and remote networks. Okay, I guess this is just a review since this is already covered in CCNA2. Okay, now all routing protocols follow the same patterns of operation. Okay, so when a router powers up, and then let's assume that you already configured the IP addresses, and then all interfaces are up. Okay, it means everything is running. All right. When a router powers up, okay, and then everything is pre-configured, it already knows. At first, no, it knows nothing about the network topology. Okay, so when you configure the IP addressing, okay, for example, let's say when you configure the IP address on this interface FA00, enter IP address 10.100 space subnet mask, enter, no shutdown. All right. So once you declared IP addresses and turned all the interfaces up, okay, that is the time when the router initially discovers its own directly connected networks. So discovering its own directly connected networks. So once the router already discovered those directly connected networks, okay, what it does is actually adding those directly connected networks to its routing table along with the interface. Okay, so you should notice, no? R1, these are directly connected networks. Why 0 hop? Why do you have 0 hop? Okay, that is because, yes, correct. These are simply directly connected networks. So you don't need to hop on the next router just to be able to reach them. That's why you have 0 hop values here. So same principle with R2. Okay, you have two directly connected networks on those particular interfaces. R3 will also have two directly connected networks. So it's just probably the graphic output of what we did a while ago when we identify the remote and directly connected networks. Okay, moving on. Okay, so what about network discovery? So how do they exactly discover the other remote networks? Okay, so let's see, no? So these are already, okay, from cold start, no? This is how they update their routing table. So first, they save the directly connected network on their routing table. So if they're gonna add entries here, it will depend on a certain protocol that you're going to use. Okay, so let's run the simulation. So when the exchange updates, all of this information will be included on that particular update, and then it will be exchanged amongst routers. Let's assume that they are using the same protocol, and that protocol is up and running properly. Okay, so right there, that is the animation. Okay, so when they exchange routing info, okay, some of this is actually the first round, no? Some of the remote networks that are not included on its original list will be added. So as you can see, no, let's just pause that for a while. The 10.3.0 network, this one right here, was learned by R1. So it was already mapped by R1. Okay, it came from R2. The update came from R2. Alright? At the same time, R2 was able to update its routing table with 10.1.0 network. That is on the other side. Update obviously came from R1. Alright, so R2 updates its routing table and added this entry on its routing table. The update came from R1 to discover this remote network right here. So let's proceed. And also 10.4.0 network on the other side. Okay, so since they exchanged on the first step, or first round of update actually. Okay, and then R3 learned about 10.2.0 network coming on this side. Okay, so right there. So R2 already has full map of the network. So a total of 4 networks. Alright. R1 has 3, so it still need more. It still need 1 in order for network conversion to occur. So which network is missing here? That R1 hasn't learned yet. Which network? Alright, if you answered 10.4.0, that is correct. Because it only learned 10.3.0 on the first round. But no worries, on the second round, okay, when they exchange routing information, okay, on the second round, the 1040 network, remote network from R3 will be included so that R1 can actually learn that and add information on its routing table as well, right? So in the same contrast, R3, look at this, doesn't have routing information on 10100 network yet. So it still lacked that one network. Okay, map. So let's see later on the second round of update. Okay, moving on. So this is the second round or the next update I was telling you about. Okay, so on the next update, so the information on its routing table are added. This time, the 10300 network was included on R1 update along with the other updates on the other side. Okay, all right. Okay. Mm-hmm. Mm-hmm. So when they exchange routing information on the second round of update, okay, you notice that R1 picked up again the missing network on the list, or that was not on his original list. All right, as well as R3. All right. So this one right here, so whenever you have this type of network, so all of the routers has learned or have learned all four networks, whether directly connected network or remote networks. So this is the time that we achieve what we call network convergence. Okay, network convergence is the term that we use in order to describe a fully functional computer networks. It means that LANs coming from this network can be able to communicate with the LANs coming on the from on that other network right there. Okay, so it is already converged. So whatever ping you do right here, we're gonna ping 1010 network, we're gonna ping 1040 network. You should expect a reply. So that means you already have a converged network, okay, or network convergence. All right, so this is what I'm telling you about. Okay, so let's see right here. No? So let's assume that this topology uses RIP-v2. All right, so RIP-v2 uses what type of metric again? Hop, correct. So let's find out. For example, 10 R1. Okay, to reach this network, how many hops? 0. To reach this network, how many hops? 0. Why? Because they are directly connected. All right. Now, in order for R1 to reach the 1030 network, how many hops does it need? Okay, correct. You need one hop. Okay, you have there 1. Okay. So again, no, hops are only occurs in between routers. Okay, so since R2 has access to 1030 network, okay, that network is directly connected to it. So R1 just took one hop in order for it to reach the 1030 network. Okay, what about 1040 network? How many hops? Okay, you have 1 and 2. That's why you have 2 hops there. Okay, so if you're going to trace the other hop sequence per network, okay, that is just the same. So this is what we call a converged network. Okay. Okay, so moving on. Okay, let's find out this time, okay, what are the different algorithms that are involved, okay, whenever a certain protocol operates or a certain protocol um, chooses how to operate. Okay, so it actually depends on the algorithm that they have. Okay, so let's start off with the distance vector algorithm. Okay, so the distance vector algorithm defines the following processes. So number 1, the algorithm provides mechanism for sending and receiving routing information. Okay, how they receive, how they send routing information, it actually depends on what algorithm do they use. Okay, number 2, they also have a mechanism for calculating the best path and installing routes in the routing table, okay, like the one that I showed you a while ago, no? Calculating paths, of course, or calculating best path, of course, depends on the protocol you are using. So again, no, if you're using REP, okay, it uses the number of hops. It compares the number of hops. If you're using OSPF, okay, cumulative, it uses cumulative bandwidth, okay, in terms of the line. Next, the third one is that it uses mechanism for detecting and reacting to topology changes. So, for example, let's say in this given topology, no, you have how many networks? 1, 2, 3. Okay, these are 3 pre-configured networks. What if this network on R2 link goes down? All right, so part of the job of the distance vector algorithm is to react, okay, and to detect first and then react to topology changes. So if this one goes down, then part of the algorithm mechanism will tell or will let other routers know that this network did go down, okay, and then just it waits for a certain time. For example, let's say if this network goes back up, then that is the job of the algorithm as well, to tell other networks that this network is already up and available again, so that other routers can update their own routing table. Okay, so what algorithm are we talking about here? So RIP, just remember the terms, okay, RIP, okay, uses Bellman-Ford algorithm. Okay, so Bellman-Ford, okay. IGRP and EIGRP uses dual routing algorithm, or also known as a diffusing update algorithm. Okay, so this is how they are actually designed. Okay. All right, so moving on with the comparison of routing different types of distance vector routing protocols. So this is just a brief review. I think we already answered this one using our activity a while ago. So these are just added information as well. So RIP, or the RIP v1, so as we all know, no, it is easy, very simple to configure. Okay, the routing periodic update is sent by default every 30 seconds. Okay, the metric used is again hop count, number of hops. Okay, and then you also have hop count limit, so it's only limited to 15 hops. Okay, again, RIP is the older version. It doesn't support VLSM. Okay, so it doesn't support VLSM. So look at this comparison right here. No, it sends routing update on a certain broadcast address. So it uses the this address to send its update. Okay, while RIP v2 uses this default address. Okay, so both of them uses the maximum number of hops of 15, and then the rest already has RIP v2 advantages. That's the reason why we actually use, if you're going to use RIP, okay, might as well use the version 2, okay, to take advantage of its features or added features right here. All right. All right. Moving on, let's have the other distance vector routing protocol, the Enhanced Interior Gateway Routing Protocol, or EIGRP. So let's see the comparison. So it's metric. Okay, again, they both use the composite metric consisting of bandwidth and delay. Right? In terms of the update, forwarded to following address. So it uses the broadcast address by default. EIGRP uses 224.0.0.10. Okay, and then the rest, okay, are all advantages compared with the other old IGRP. So the VLSM, CIDR, auto summarization, and then the authentication as well. Okay, so in terms of its feature, all right, so this is how EIGRP sends update. So it's actually different from RIP, okay, because it has these terms that it uses, okay, in order to send the different update now in terms of its routing information updates. Okay, number one, it has bounded triggered update. So it's more like a semi. Okay, you remember OSPF being triggered update. This time, when EIGRP uses bounded triggered update, so it's more like semi OSPF. We can consider it as a semi OSPF. All right, so bounded triggered update means it only sends update only to routers that need it. So it doesn't flood your line with a periodic update. Okay, even if that particular router does not need any update because there's no changes in the topology. Okay, next, it uses hello messages, okay, to maintain adjacencies. So to check on a certain networking neighbors, it doesn't send the entire routing information update. So it's just a hello keep alive mechanism. Okay, maintains a topology table, okay, routes that is received from its routers, and then keep it on the topology table. So it's more like a pure update here. The other one is rapid conversion, rapid convergence. Okay, rapid convergence. So as we saw a while ago, no, in terms of its convergence capability, no, EIGRP is faster compared with RIP. All right, and the last one is that it supports multiple network layer protocols. All right, so actually it extends up to layer 3. Okay, yeah, something like that. So it has this added features, functionalities that makes it better, but at the same time makes it complex to configure compared with RIP version 1 and version 2. Okay. Okay, lastly, okay, let's take a look at link state, dynamic routing, and then see how this protocol behaves, okay, what algorithm is used in this particular routing protocol, and also the process or the metrics that this protocol use. Okay, so let's have the discussion. Okay, so we have link state. So we all know that link state routing protocols, also known as the shortest path first protocols. Okay, its algorithm is built around, look at this, Edger's Dijkstra. All right, so we call it the Dijkstra. It's pronounced as Dijkstra algorithm. Okay, SPF algorithm. All right, so OSPF stands for Open Shortest Path First. Okay, these are the two link state routing protocols under IPv4, the OSPF and the ISIS. Intermediate system to intermediate system. Now, in CCNA3, okay, again, no, we're only covering RIP V1, RIP V2, RIP V1, RIP V2, EIGRP, and OSPF. Okay, unfortunately, ISIS is beyond the scope of this curriculum. Okay, so we're going to focus on OSPF on the succeeding modules. Okay, because it has different discussion. Okay, different module. Okay, so let's see how the Dijkstra algorithm works. Okay, look at this. Shortest path first, it means, no? So we all learned that OSPF uses cumulative bandwidth, no, as metric. Okay, we call it the cost. Okay, cost. Costs are actually configured by default, and the cost is actually depends on the line that is being used. So they have an equivalent. They have an equivalent value in terms of cost. But when you configure OSPF and then you wanted to, let's say, okay, you wanted to customize network flow. Okay, we can actually change the cost value per line. All right, remember that, no? So when we are already on the configuration part, okay, that is on the next module, no? We have an option to change the cost value inside OSPF on a certain link. All right. So in this scenario, let's assume that the following cost values are already pre-configured. Look at this one right here, no? So let's say if you're going to, okay, the path here is coming from R2, okay, R2, okay, to reach R3 LAN. So this would be our source. Okay, let's assume that this will be our source. And our destination is on this network right here. Let me zoom in on this one. All right. So this will be our source right here. Okay. And then our destination is the R3 LAN. This one right here. So this will be our destination. This will be our source. So if you're going to count or to the digital algorithm works this way. No, it compares the cost, okay, amongst the line, okay, the configured cost within the line, adds them, and then whichever is the lowest in terms of cost, it declares it as the shortest path. Okay, it's like going from point A to point B. No, point A to point B, you have two separate options. Okay, but the first option is shorter compared with the other option. So it's like going to the store, right? So from home, for example, let's say you're gonna go to from your home in the O, you're gonna go to SM Clark. So you have several paths available. All right, so you can probably take the expressway and like South Gate. You could take the main road, or you can take the perimeter road. So the Jigsaw algorithm works by comparing the path in terms of its cost, okay, and then um, it chooses the shortest path, okay, the shortest possible path. So in this scenario, so we have from R2 to R3, we have several options. So we have it can go this way, it can go this way as well, no? If you're going to go this way, so let's just count the number of costs. So from R2 you have 10. Okay, from R5 to reach R4 you also have 10. That is already 20. Plus 10% is 20. So from R4 to reach R3, all right, you have 10. And then to reach to reach the network rider, you're gonna add 2. So you have 10, 10, 10. You have 32 in total. Okay, 32, right? Now, let's compare that with this path right here. So you have 20 or 1, you have 5, 25, plus 2, you only have 27. So how much is the cost? Okay, when you have this path right here, you have 32, right? 32. So obviously, all right, obviously, okay, 27 algorithm, the Jigsaw algorithm will compare the cost, and definitely it will see that 27 is less than 32. So instead of taking this path, okay, the Jigsaw algorithm of OSPF will always take the shortest path first, which is this path right here. Okay, depends on the cost value. All right, so that's how actually that's how the Jigsaw algorithm actually work. Okay, it uses the accumulated cost along each path from source to destination. Okay. Okay, so moving on with another SPF3 topology and cost for each LAN example. Okay, so let's assume that in this example we have our R1 as our source, and then let's try and check the cost. So we're just like adding numbers here now. 1 plus 1. Okay, to find out the total cost. Okay, and to determine the shortest path. So for example, let's say R1 going to R2 LAN. Okay, what is the cost? Right there, 20 plus 2, that gives you 22. Okay, R1 going to R3 LAN, right here, 5 plus 2, that gives you 7. R1 going to R4 LAN, so you have two possible pathways. So you have this path right here, that is 5, is 10, plus 2, that gives you, 5, 10, 15, plus 2, that gives you 17, while the other path gives you 20 plus 2, that is 22. So if you're going to compare the two paths, 17 is the shortest. So that is written right here. R1 going to R5, just erase this one. R1 going to R5. So you have how many paths available. So you can either go this way, one available path, and then the other one right there at the bottom. So you have R1 going to, or you also have this one right here. No? You have 3 possible paths to reach this destination right here. So which one of them is the shortest path? So you have, let's analyze. No, let's start off with this one: 20, 10, 30 plus 2, that gives you 32. Okay. Next you have 5, 15, all right, plus 10, that is 25, plus 2, that gives you 27. Just list that down. Sorry for my writing. Huh? Then the last path, you have 20 plus 10, that is 30, plus 2, that also gives you 32. So if you're going to compare those 3 costs, so which one has the lowest path? Obviously, 27. So you see, no? This is how the Dijkstra algorithm works, okay? Or this is how shortest path first actually works, okay? So it depends on the cost, accumulated cost, no, in choosing the best possible path, okay? Whenever you have multiple paths. Of course, when you only have one single path, okay? Let's say, for example, to reach R2, no, it is obvious that uh, you have this line right here, no, from R1 to R2. But in case there will be shorter path, okay, let's say you made this around, let's say 70 or 60, okay, even if it only takes one hop to reach that network, when the other paths has lesser cost, okay, then OSPF doesn't mind that. Okay, it still follow the shortest cost policy. Okay, so that's how uh, the SPF3 works, or the algorithm, the digital algorithm under OSPF works. All right, so yeah, so last few slides. Okay, so this time we're gonna just try and identify the different advantages of link state routing protocols. That's why it's considered as the widely used, okay, protocol, especially for medium to large size networks. No? So the first one is that number one advantage is router builds its own topological map of the network to determine the shortest path. Okay, so like what we have in our scenario a while ago. It has faster convergence because of the exchange of link state protocols updates, or link state protocol update. It's like the hello packet from EIGR, all right, and it's a triggered update. So it only sends a certain update. OSPF only sends that update whenever necessary, or whenever there's a change in the network. So it doesn't send it periodically compared with RIP V2. All right, so yeah, that's it. No, LSPs are only sent when there is change in the topology and contain only the information regarding that change. So it doesn't necessarily contain the entire routing table. Okay, so it only has the information on the affected network information. Okay, so that one right there. And also, it is used on hierarchical design when implementing, especially what we call multiple areas. So it OSPF actually has certain variation wherein we can create multiple areas. Okay, we call it multi-area OSPF. Okay, we're gonna discuss more on that and how to implement it on the succeeding modules. Okay, disadvantages of LSP. Okay, number one. Okay, so you can see it there, no? In terms of its resources, memory requirements, no? It requires additional memory to create and maintain the link state database. Okay, it also has processing requirements, so it consumes a lot of CPU overhead. That's why it is not recommended for old routers. Okay, in terms of bandwidth requirement as well, okay, probably it occurs during the initial startup of routers. Okay, but when you already have a stable network, then it might not be a problem. Okay, but in terms of unstable network, it might become an issue in terms of uh, bandwidth that is being adversely affected by the exchange of link state protocol updates. Okay. All right. So I guess that ends our fourth module. Just in case we're gonna have a live session, or if there will be added information, because this video is taking too long. I'm just gonna post an additional information on our Edmodo or NetAcad class announcements. All right. So again, thank you guys for listening. I hope you learned something. Right? You learned the principles behind or the theories behind the dynamic routing protocols. Okay, the succeeding chapters or modules will now focus on the configuration part. All right. Namely, we're gonna do RIP V2, EIGRP, and OSPF. Now that we already understand how this dynamic routing protocol works, okay, in and outs, okay, how they exchange information, how do they achieve convergence, okay, what are their advantages, disadvantages, comparison. Um, Once you configure them, okay, or apply it on a live network, then you already understand the principle behind it. Okay, that's the purpose of this module. All right. So yeah, thank you again, guys, and see you on the next one. Goodbye.